Okay, welcome back again. Welcome to my channel. Today we will see some examples on momentum application and channel transitions. So let us see example 2.4 momentum application. A hydraulic jump is formed in 5-meter wide outlet at short distance of control gate. If the flow depths just upstream of the gate and downstream of the sluice gate are both 10 meter and 2 meter respectively, and the outlet discharge is 150 meter cube per second, determines the flow depths downstream of the jump, the thrust force on the gate, head loss in the jump, and power lost due to the jump, the length and the height of the jump, and the percentage of energy lost due to the jump, and the efficiency of the jump. Now let us see. So first we are given the width of the channel, which is 5 meter, and also you have the upstream and downstream water depths given, and outlet discharge is also given. So what it will be the flow depths downstream of the jump, So this is the free body diagram, which is just according to the given parameter. You have upstream water depths, which is 10 meter given, and downstream water depths you have 2 meter. Then you have to draw the hydrostatic force diagram, which is triangular distribution like this. Then you have to compute again V1, Q is already given, and F2, which is this one. And the force on the gate will be to this direction. So we will apply momentum principle and hydraulic jump equation, which is y2 over y1 is equal to half of -1 plus 1 plus 8 Froude number 1 square. So we will check the Froude number at this point, whether it is supercritical or subcritical flow. Let us see calculation. So for rectangular channel, you have this equation, which is V naught, which is upstream of the gate. You can calculate V naught, which is Q over area. So Q over area, V times Y naught, will be 3 meter per second. Then V1, once you have velocity, then again V1 should be computed. Since Q is given, so you can have 150 divided by 5 times 2, which is 15 meter per second. So Froude number, you can calculate now. Froude number, you can check Froude number whether subcritical or supercritical below the gate. So V1 is already known, 15 divided by square root of 9.81 times 2, then 3.386, which is larger than 1. So since it is greater than 1, supercritical flow. Then jump will be formed downstream of the gate. Then what will be the subsequent depths after the jump? What will be the post-jump depths? Y2 over 2 is equal to 1 over 2 -1 plus square root of 1 plus 8 times F1 square. Then Y2 will be this result, 8.63 meter. Then according to momentum principle, the net force is equal to the rate of change of momentum, which is summation of force in x direction is equal to mass flow rate, then times change in velocity V2 minus V1. So mass flow rate is rho Q, then V2 minus V1. Then you can have all forces, you can just sum up F1 to the right, which is F1 minus F2 to the left, according to the free body diagram, according to this one. F1 is this one, this direction, F2 is to this direction, then Fg again, just it is a resistance force on the gate, then you have to have minus Fg, rho Q, V2 minus V1. So we know continuity equation again, V is equal to Q over area, Q over A2, Q over A1, then you will substitute. So force is equal to pressure times area, because pressure is force over area. Pressure is, we know pressure equal to force over area. Then instead of force, you can just crisscross. So the pressure force multiplied by area. If you just make crisscross here, you can find P times area. So P1 times A1 minus P2 A2, then minus Fg is equal to rho Q, change in velocity. So P1 is half gamma Y1 times A1, then minus half gamma Y2 A2, minus Fg. Then you can substitute now rho Q square, Q times Q, since Q is constant. Then you can substitute here. Then finally, we can arrive at this equation, which is the change in momentum, which is the force on the gate. Then finally, you can multiply by unit weight. Then A1 first, you have to compute A1, which is 5 times 10. 5 is the width of the channel, 10 is the depth of water, 50 meters square. Then 5 times 2, again, for the second area. Then Y1 bar is just half of the projected depth of Y1, which is 10 over 2, 5 meter. Then Y2 bar again, Y2 over 2, which is 2 over 2, 1 meter. Then finally, you just substitute in this equation, then the force on the gate will be this magnitude, 554.4 kilometer. If you multiply by unit weight, you can take out this unit weight common, then you can multiply. Then finally, 554.4 kilometer. This is the force on the gate. Then again, you can have energy loss, which is HF. Change in energy is Y2 minus Y1, the whole cube over 4Y1, Y2. Then finally, change in energy will be this one, then 4.22 meter you can find. Then power loss due to the jump is gamma Q times change in energy or the energy loss. If you multiply, then unit weight is 9.81 kilonewton per meter cube, then we will find in kilowatts. This is the power loss due to the jump, 6,209.73 kilowatts. And the length of the jump and the height of the jump can be computed like this. Height of the jump is the difference in sequent depth and Y1 before jump and after jump. Then you have 6.63. And length of the jump is mostly 6 times height of the jump. Then if you just calculate 399.78 meter, this is the length of the jump. And the percentage of energy lost due to the jump and the efficiency of the jump will be percentage of energy lost is change in energy, which is the loss, divided by original energy, which is upstream energy, then 31.33%. This is the percentage energy lost due to the jump. And the efficiency of the jump already E2 divided by E1. You can calculate. So E1 is this one, and V2 is this one. Then finally E2 will be just Y2 plus V2 square over 2G. You get this one. Then efficiency of the jump will be the ratio of the second energy divided by the first energy. Then you can use this equation, or you simply divide this one. Then 65.39%. This is just the efficiency of the jump. Okay, now let's go to channel transitions. Channel transition with a hump. A rectangular channel has a width of 2 meters and carries a discharge of 4.8 meter cube per second with a depth of 1.6 meter. So you have Y1 depth, and at a certain section of a channel, a smooth hump with a flat top of height 0.1 meter is proposed to be built. Calculate the likely change in water surface. What will be the change in water surface? Neglect energy loss. So the first step to do this problem is you have to know the regime of flow. So let's the surface 1 and 2 refer to the upstream and downstream of the sections respectively. Then, as in the figure 2.9, we will see, then discharge intensity is equal to, you have Q is equal to capital Q divided by B. So capital Q, which is discharge 4.8 given, if you divide by bottom dimension, you get 2.4 meter cube per second per meter width of the channel. Then V1 is 2.4 over 1.6, which is just small q divided by Y1. Then V1 square over 2G again, this one. Then we can compute specific energy at section 1. So this is the specific energy at section 1, E1. Then you can compute, then finally you have to compute the fluid number again. So channel transition with a hump is just if there is subcritical flow in the upstream section, there is a drop in water surface. Otherwise, if it is supercritical, there is a rise in water surface elevation. So E1 is given by this equation or this equation. E2 is this one. Then for up step, you can see now E2 will be E1 minus del Z. So E2 is from here up to here. Then you have to subtract del Z. Since E1 is up to this point, E1, then E1 is E2 plus del Z. Then this one, E1 is E2 plus del Z. Then E2 will be E1 minus del Z. So del Z is given, then E2 can be computed. But first, let us see the full number, which is in the upstream V1 divided by square root of GY1, 0.391. Hence, the upstream flow is subcritical. The hump will cause a drop in water surface elevation, since it is a subcritical flow. Then at section 2, E1 is just you have Y1 plus V1 square kinetic head plus depth of water. You have this one. Then E2 will be E1 minus del Z. So E2, once you compute this depth, which is 1.615, then we can compare with critical depth. Critical depth is Q square over G, the whole 1/3. Critical depth, which is this one. Critical depth is 0.837. Then what is the critical specific energy, which is 3 over 2 YC? Then you can get this is 1.256. So we know already, we have calculated just F1, which is the full number in the upstream section of the channel, which is subcritical. Then there is a drop in water surface elevation. So what will be Y2? So the minimum specific energy at section 2, which is EC2, is less than E2. So since EC2 is less than E2, according to the above calculation, so the available specific energy at that section, which is hence Y2 is more than YC. Y2 is more than YC, and the upstream depth Y1 will remain unchanged because just Y2 is more than YC. Then the depth Y2 is calculated by solving the specific energy. Already we know E2 is this one, 1.615. Then you simply substitute discharge in Y2. Then by iteration, just you can solve. So Y2 is cube root of 1.615 times Y2 square minus this one. Then by iteration, you can give any arbitrary number, say 0.9 equal to in your calculator. Then it will be saved in your answer in your calculator. Then make your calculator on again. Then write this expression without any equal sign. So you have already saved as answer this number. Then continuously you can click equal until you get constant number. Then the constant number will be your last iteration. The number of iteration is just it depends. So the number of iteration depends on the initial guess. You give an arbitrary number. So just try to give just according to y2 depths, maybe larger than 1. So this is just you have y2 1.481 meter. This is the second depth. And in example 252, in the above example, in example 251, if the height of the hump is just 0.5. Initially it was something 0.1 or let me check. Yeah, 0.1. Initially it was 0.1. So if you increase the depth or the step height or just the height of the hump to 0.5, estimate the water surface elevation on the hump and at a section upstream of the hump. What will happen? So let us see. F1 already we computed 0.391. E1 already we have computed, and YC is equal to YC2. Then you have 0.837. Then available specific energy at section 2 is equal to E1 minus del Z. So del Z is already given. What will be the specific energy at section 2? Since we know E1, since it is upward step, you will use minus, then 1.25215. then AC2 will be 3 over 2 of YC2. Then you have this result 1.256 or D. The minimum specific energy at section 2 is greater than A2. The minimum specific energy at section 2 is greater than A2. 1.256 is larger than 1.215. So the available specific energy at that section, then hence the depths at section 2 will be at critical depths. At critical depths, thus E2 will be AC2, which is this one. Then the upstream depth Y1 will increase due to the increment of the hump. Then the upstream depth will increase to Y1 prime. It will go something, elevation will increase, such that the new specific energy at the upstream section 1 is just going to be computed. Now let us see E1 prime is equal to AC2 plus del Z. So once you have this one is upstream, just new energy, then you have to substitute del Z. Then finally, Y1 prime, which is the new depth, will be computed by iteration. If we substitute the values, then we get this equation. Then by iteration, again, you can use calculator. Then it will be Y1 prime will be 1.648. So it is increasing. Then solving by try and error and selecting the positive root, which gives Y1 prime is more than Y2. Y1 prime is larger than Y2. So the nature of water surface elevation is shown here. You can see energy line after the placement of the hump, then it is just increasing. So Y1 prime, so it will be from Y1 up to Y1 prime. So this is E1 first, then E1 prime will be going up. So this is water surface elevation. Y2 will go to YC2, 1.256. This is del Z. If del Z is increasing, then there is something increment in the upstream of the channel. So the depth of water is increasing. So chocking sometimes in case of the channel with a hump, and also in case of with constriction, hump and constriction, it is observed that the upstream water surface elevation is not affected by the conditions at section 2 till critical stages just achieved. Till critical stages achieved. So chocking, let us see in this example again, channel transition with constriction. A rectangular channel is 3.5 meter wide and conveys a discharge of 15 meter cube per second at a depth of 2 meter. It is proposed to reduce the width of the channel at a hydraulic structure. So from this width, it is just going to be decreased. Assuming transition to be horizontal and the flow is to be frictionless, determine the water surface elevations upstream and downstream of the constriction when the constricted width is 2.5. From 3.5, if you reduce to 2.5, what will happen? Again, if you release more to 2.2, what will happen? Now let us see. Let suffix 1 and 2 denote sections at upstream and downstream of the transition of the channel. Then discharge is Q is equal to area times velocity, V1, Y1, V1. Then V1 already you compute. Then let us calculate the Froude number. Froude number is, since it is a rectangular channel, you can use this formula, which is V1 divided by G square root of G Y1. Then you get this result, which is 0.484. So the upstream flow is subcritical. So if it is subcritical, and the transition will cause a drop in water surface elevation. So you can compute now. So E1 will be Y1 plus kinetic head. Then you substitute the values. Then you get this result. Then once you have this one, then let minimum width at section 2, which does not cause chocking. Then let us calculate ECM, which is the minimum specific energy is equal to E1, 2.234 meter. Then you can have YCM, 2/3 of ECM. Then you have Y critical depth, this one. Then you have to compute using this equation the minimum width at section 2, which does not cause chocking. This is the minimum width, which is 2.6 2.36 meter, but we have provided 2.5. So when B2, which is 2.5, which is minimum or smaller than the minimum available, hence chocking will prevail. Chocking condition will prevail. So the depth at section 2, which is Y2 is equal to YC2, the upstream depth Y1 will increase due to the constriction below the minimum. We are just constricting. So the depth at Y1, which is at depth at section 1, Y1 will increase to Y1 prime. So Y1 prime should be computed. So actual Q2 you can find 15 divided by 2.5 actual discharge divided by width of the channel 6 meter cube per second per meter. The critical depth at section 2 is 1.542. Then specific energy again 3 over 2 of YC. Then you have 2.3136 meter. At the upstream section, E1 prime reach to EC2, which is just the critical specific energy at section 2, which is this one, with the new upstream depth of Y1 prime such that you have Q1 Y1 prime V1 prime is equal to 15. Then divided by width of the channel, you have this equation, which is Q1. Then let us compute now Y1. Y1 prime plus V1 prime square over 2G will be this specific energy. Then once you have this one, then you can just substitute Q square over 2G Y1 square. Then you have Y1. Then solving by trial and error for this equation. For this equation, you can find Y1 prime will be this dimension. So this is just, there is just a depth change. So when B2 is again reduced to 2.2, this is also more less than. B2 is already given. Then if it is 2.2, what will happen? Chocking condition will prevail. So depth at section 2 will be Y2 is equal to YC2. Then you can find Q2 again, find Q2, which is this one. Then what will be the new depth again? Let us calculate. YC2 critical depth at section 2 is this one. Then EC2 will be this one. Then at upstream section, new upstream depth Y1 prime and E1 prime is equal to E critical, which is 2.519. Then Q1, which is V1 prime, Y1 prime, only for rectangular channel. Then you can have this one. Then you can substitute Q1 square instead of V1 square, Q1 over Y1 square. You substitute. Then again you iterate this. Then you will have, so just you can solve by try and error this simplified equation. You have Y1 will increase again 2.350. So when the width of the channel is more, just when the width of the channel is going to be reduced more, then you are increasing the depth of water in the upstream section. Let us see the pictorial presentation. I think this is as exercise you can try. Just answers are given here. So you have just discharge, specific discharge given, depth Y1, upstream of the step is this one, upward step height is this one. Assume rectangular channel, determine the upstream Froude number. You calculate Froude number, then E2, then downstream depths, determine absolute change. I think similar. So this is the example already. The second problem already we have solved, but you can try this one as exercise, as assignment. So assignment problems you have again. This is a rectangular channel which carries a discharge of 20 meter cube per second with 5 meter wide, and also you have a depth already given. So the width beyond a certain section is to be changed to 3.5, reduced just from 5 to 3.5. Then you have to compute the minimum width that will just that will not cause chocking. If it is desired to keep the water surface unaffected by this change, what modifications are needed to the bottom of elevation? So del Z should be computed. And the second assignment is find the alternative depths corresponding to a specific head of 2 meter and a discharge of 6 meter cube per second in trapezoidal channel bottom dimension given, M given, triangular channel also you have. So alternate depths you can calculate since specific energy is given by the depth of water plus just Q square over 2G A square. So according to this, you can calculate the alternate depths. You have a specific head already given, discharge given, and channel cross sections are given. So for circular channel, by try and error or just you can use table as previous, you can try. And this is again the same, you have to compute specific energy and alternate depths. Already you have Q and bottom dimension given, and the depth of the flow is already given. So you can just use, you can iterate. This is also a triangular channel with apex angle of 60 degree and carries a flow of this one. And the depth of this is the flow subcritical or supercritical. We can check, which is a Froude number, which is V over square root of G times D. D is the hydraulic depth for triangular channel, area over top width. Then what is the critical depth, etc. You can try. So this is just as assignment you can try. So okay, so this is all about today's tutorial. Hopefully you liked the video. If you have any comment or doubt regarding this topic, please let me know and write down in the comment section below. I will definitely reply on it.